now that we have seen the convergence between polar and Cartesian coordinates, our next goal will be porting to the polar context of all the things we could do with Cartesian coordinates. So the thing to start with will be dealing with curves in polar coordinates. So first we need to think about what is even a curve and how do we write down a curve in polar coordinates. So the way to do it will be described by the following definition. So a polar curve is a set of points, of course, in polar coordinates, that satisfy the following equation. So we will primarily deal with equations of the form r equals f of theta. So if you compare this equation to what we would normally have for Cartesian curves, then for such curves, we would normally deal with y equals f of x. So one of the coordinates is a function of the other, and so this is similar to what we do for the polar curves. We say that a polar curve is the set of points for which the r coordinate depends on the theta or the angle coordinate. And so to give you some quick examples, let us look at example 5, in which we will determine which curve is given by r equals, say, 5. So let's think about this equation. We have r equals 5. In other words, the radius, the polar radius, is constant. It does not depend on theta. So we're interested in points with coordinates r theta where r is equal to 5. What does that mean? Well, it means that if we draw the coordinate axes, so let's say we have two coordinate axes, but this is the polar axis and this is the origin here. Then points that have r equal to 5 are precisely those from which the distance to the origin is equal to 5. If I connect any such point to the origin, it will be 5 units away. And vice versa. Any point that is distance 5 from the origin satisfies this equation. So, in other words, the set of points which correspond to this polar equation is precisely shown in blue here. So they are the circle of radius 5 centered at the origin. And so here we have an elegant way to write the equation of this circle, whereas in Cartesian coordinates we would have to do something like this. This circle would have the equation x squared plus y squared equals 25. So the polar equation ends up being much more compact. Another curve that can be written in polar coordinates in an elegant way is given by the following equation. So let's identify the curve for theta equals, say, pi over 6. And so we will start by specifying the polar axis here in the plane. We have a polar axis, we have the origin. Then the set of points are theta with theta equal to pi over 6 have the form r pi over 6, where r can run anywhere on real numbers. So how do we arrive at the set of all such points? Well, we can take the polar axis. So take the polar axis like so and rotate it by the angle pi over 6. So let's place another polar axis on top of this one and then rotate it. Okay, so here we have, say, the angle of pi over 6. Angle between these two positions is our theta, and so we see that we get the entire blue line in this way. So for different values of r, we run back and forth along this line, so we get completely the entire blue line here. So in polar coordinates, its equation will be theta equal to pi over 6, whereas in Cartesian coordinates, we'll get something of the form m times x, where m is the slope of this curve. Now, how do we determine the slope? Well, if you recall that m slope is equal to the tangent of the angle that the line forms with the polar axis. So that's tangent of pi over 6, or 1 over square root of 3. And so the equation of our curve in Cartesian coordinates will be 1 over square root of 3 times x, like so. Let us talk about a less elementary curve now. In the next example, where we will identify the curve given by the equation r equals 2 cosine theta. So here we can in fact restrict theta here, or for any of the previous curves. We do not need to allow theta vary on the entire real line. It will in fact be enough to only look at thetas between 0 and 2 pi, because that is the period of the angle. And so in this case, we capture the entire curve by letting theta vary between 0 and 2 pi. And this will be often the case in subsequent curves. Okay, so how do we identify this curve? So the easiest method of identification to us is to rewrite this curve in terms of its Cartesian coordinates and then try to recognize it there, because we have a fairly large toolbox of curves in Cartesian coordinates that we can recognize. And so the hope is that once we convert this to Cartesian coordinates, we can deal with it. In order to convert to Cartesian coordinates, recall the conversion formulas that connect Cartesian coordinates x and y to the polar coordinates. And so x in terms of polar coordinates is r times cosine theta, and y is r times sine theta. Great. So as you see, here we have 2 times cosine theta. We do not have r though. So if we take this equation and multiply both sides by r, then we will indeed obtain r cosine theta on the right. So we'll have r squared equals 2r cosine theta. So this part on the right gives us precisely x, and this part on the left can also be easily expressed in terms of the Cartesian coordinates. So since r is the square root of x squared plus y squared, this is another conversion formula. So these are all conversion formulas that we discussed previously. In view of this formula, we have for r squared that it is equal to x squared plus y squared. And so then we conclude that the equation of our curve in Cartesian coordinates is x squared plus y squared equals 2x, like so. Great. Now this is purely in terms of Cartesian coordinates. So let's go ahead and try to recognize this curve. So to do that, we will need to complete the square here. So we will write it as x squared minus 2x plus y squared equals 0. And so to complete the square for the first two terms, we have to add and subtract 1, so that we have x squared minus 2x plus 1, and then minus 1 because we want to keep the equality. And so the first three terms together are a complete square. And then we have plus y squared equals 0. So the first three terms amount to x minus 1 squared. And then I'll have a plus y squared, and I can put the minus 1 in the right hand side with the minus sign, like so. So I have x minus 1 squared plus y squared equals 1. And this is the Cartesian equation of the circle centered at 1, 0. So this is the point in Cartesian coordinates here, with radius equal to 1. So indeed, if you recall, equation of a circle in Cartesian coordinates it is of the form x minus a squared plus y minus b squared equals r squared. And so equating the corresponding coefficients, here we have that a is equal to 1, b is equal to 0, and r is equal to 1. And so this corresponds to a circle of radius r with center at AB. Great, and so we conclude that our polar curve over here is the circle of radius 1 centered at 1, 0. And so as an exercise, let me ask you this. What is the curve that corresponds to r equals to 4 sine theta in polar coordinates? And so all I did here, compared to the previous example, was I replaced cosine with sine and 2 with 4. So if you argue in a similar way to what we did over here, you will see that this also corresponds to a circle, albeit with a different center and a different radius.